guys, let's start. Everybody. Lucy's note up here. Take note of that before I erase it. Her sessions. What is that? That was tonight at 7 p.m.
Yeah. We're done with your sheet? 6:30. It's 7 today, but it's 6:30 tomorrow.
And this is tomorrow. Okay. So take note if you want to go to those. Okay. I do have a quiz up on electron configurations. And I thought we were so far ahead. That's because I thought we had done electron configurations. Everybody? You guys? So I'm kind of backing up a little bit. That's a way earlier chapter. Electron configurations. Yeah, 3.3 and 3.4. But let me describe it to you, and I think I have the only questions you'll need to be able to answer on this are on D2L. But so we've talked about this much about an atom. Back when we started talking about atoms, you've got your proton in the middle, you've got neutrons in the middle, and you got electrons that are in the outside. And that's all I said about the structure. But we do know a lot more about how electrons build in the structure of an atom. So those shells, as we call them, that get built out, we can assign where electrons are within an atom. The way I always do this, and books don't seem to do it this way anymore, the way I diagram it, but I'm telling you it's the best way to do it. An electron configuration, anytime you get, okay, here's an atom, give me its electron configuration. The first thing I want you to think is say this to yourself, 1, 1, 3, 1, 3, 5. What I mean is 1, 1, 3, 1, 3, 5. I tell you to say that to yourself just so you can turn around and draw that on a piece of paper real quick. I'll try to make it a little more straight across. 1, 1, 3, 1, 3, 5. And then turn around and draw this structure on a piece of paper. From there, it's extremely easy. I want to show you what this is diagramming of. There's really kind of no axis down here, but it's a diagram the further you go up. It's the further you're getting away from the nucleus, meaning here's a nucleus, and if I just pick a radius about that far, I went, okay, there's one radius around the nucleus. There's a shell where electrons can go. And let's say the nucleus is down here. That's this distance. And then further out, there's another radius that goes out here. So a little further distance from the nucleus, there's another place where electrons go. That's here. And this next one with 3, that one's just real close to this. They really do go together. We call these circles orbitals. So there's one orbital here, there's two here close to each other, and then there's 3. I know the scale isn't really the same as far as these gaps go, but out here, if I drew a whole circle, and then another whole circle, and another whole circle, there's a 3 that goes with these 3. So this is really showing you a distance from the nucleus. And having said that, you can kind of forget this. Don't forget it, but you don't have to think in terms of this diagram. Let me Here. Let's do.
Yeah, I think it's almost like detailed.
Okay, a little piece of the periodic table will help us. I don't think I messed it up. Okay, a little bit of the periodic table. Okay. If I ask you, I want you to draw me or give me the electron configuration of some atom, what's the first thing you think? Yes, I'm telling you, do it like this. 1, 1, 3, 1, 3, 5. Say that to yourself, and you turn to a piece of paper and you go 1, 1, 3, 1, 3, 5. The rest is easy. I do want one more thing on the This is 1. This is 2, 3, 4. 12. Yes, 16. 34. So I'm going to get the atomic numbers on here, then I'll be ready. Because you're always going to have that periodic table. 19, 20, 21, 22. So these are just a few transition levels right there that I wanted to include. 21, 22, 23. They'll probably can't be. Okay, now let me start again. Let's say I wanted you to do the electron configuration of, oh no, let me tell you one more thing about this diagram. Once you get the 1, 3, and the 1, 3, 5 in there, realize that this goes by itself, these two go together, these three go together. And you can continue this. There's 1, 1, 3, 1, 3, 5, and then there's 1, 3, 5, 7, and there's actually 1, 3, 5, 7, 9 above there. But we're going to stop there. I'm not going to tend to have you do those bigger ones, but that's the pattern. They actually do build like this around an atom. The first shell is just this one thing. The second shell has this one thing and then this triple thing. The third shell has this one thing, this triple thing, and this 5 thing. And then the fourth shell has 1, 3, 5, 7. So that pattern continues. So just realize that pattern's there. That's why I had to go 1, 1, 3, 1, 3, 5. But there is a 1, 3, 5, 7 above there. I just haven't drawn it. Okay, so from there, realize there's some labels to put in. Historically, from spectroscopy, early spectroscopists used S, P, D, F. I think they're actually always lowercase. So I can't give you a good pattern there, but they could have done A, B, C, and D, but they just called it S, P, D, and F. Okay. The S types are these single ones. Those are S, and then there's another S above here. The second one is called P, so these are the P types. So if you'll just memorize this, then everything will be easy from there. The triples are the P types. This one with 5 is the D types. That's my lowercase d. So 1 orbital there, 3 orbitals there, 5, and the F, 1, 3, 5, 7. So there's a 1, 3, 5, 7 above there. Okay. So there's that. And then I told you this one goes by itself, these 2 go together, and these 3 go together. We just call this one the first shell, 1. This is the second shell, so this is 2S, 2P, 2P, 2P. These are all 3s, so that's 3S, 3P, and 3D. So in terms of distance from the nucleus, this is how the shell is built. Okay. Now I can show you how easy this is. So 1, 1, 3, 1, 3, 5, and then remember the single ones are S's, the triple ones are P's, and when there's 5, there's D's. If you ever drew one that goes as far as the F's, that would have 7 across and they would be F's. Okay. Now, what if I said, give me the electron configuration of phosphorus? All you have to do is look on there, and I do mean the neutral atoms here. If you have phosphorus, and you go, okay, it's got 15 protons, that means it's got 15 electrons, and you do it like this. To put the 15 electrons in here, you go 1, that's supposed to be an up arrow, 2, I'm counting to 15, 3, 4. Now watch this, when I do these that are straight across from each other, I went 1, 2, 3, 4. Now I'm going to go 5, 6, 7. Now I'll go back and pair them up. 8, 9, 10, 11, 12, 13, 14, 15. That's the electron configuration of phosphorus. If you can get this diagram in front of you, all you have to do is count up. The rules I'm following is, for the single ones, I just go ahead and pair them as I count. Then I go up to the next one, I keep counting. When you get to somewhere they're straight across, you do them single first, and then you come back and pair them. These are electrons pairing in the orbitals. Then I got to this one, I just did them both. Then I started counting across, and then when I ran out, I just stopped. That's the electron configuration of phosphorus. You with me? The thing about this, there's more than one ways to represent that, but if you have this in front of you, it's all easy. I call this the inverted Christmas tree diagram or something. I don't know what they called it back in the day when I learned this. But that's the most intuitive way to do it. The rest is easy. You sometimes see this. That's one way to represent phosphorus. Another way is a lot of books seem to be doing this now. There's the 1S. There's the 2S. There's the 2P. Next is 3S. And then 3P, and I'll be able to stop there. And then it's just like these arrows. There's another way to represent the electron configuration of phosphorus. But I literally just built that looking at this. So books seem to be doing that boxy thing these days. I think this is good because it shows you distance from the nucleus, so at least there's something being diagrammed there that this one's not. Okay. And okay, so here's one way to show phosphorus, another way to show electron configuration of phosphorus. Here's another way to show it. Frequently it's like this to start with. And then you go 1s2, 2s2. So again, I'm using these labels, but the 2 here represents how many electrons are in it. So 1s2, 2s2, 2p6, because there's 6 in there, 3s2, 3p3. There's another way to do the electron configuration of phosphorus. Totally redundant, but books don't seem to do this anymore. I see this more in books these days. This is kind of the way a professional chemist will put it. So they would probably write this. Or actually, there's one more way to do it. You could do it like this. Well, let me back up and go, what did I do, phosphorus? Let's just stop with phosphorus and let me do neon, one of these noble gases. And then I'll show you what this last plate together is. So it said, do the electron configuration of neon. What's the first thing you do? You think to yourself, 1, 1, 3, 1, 3, 5. And you build that diagram. Then you go to the periodic table and you look at neon and you go, 10 protons, that means neutral neon has 10 electrons. And you follow the pattern while you count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's the electron configuration of neon. And I could do that if I wanted to. It's exactly the same way I did it. I could do this if I wanted to. Exactly the same way I did it for neon. But what I want to point out is, when the 1 in the 3 part of any given shell is full, it tends to be, then you've got one of those noble gases. The only weird one is this one, because that's the only orbital there in the first shell. Once those 2 are full, you have helium. But really, for this discussion, let me take helium and stick it over here. Because for this discussion, helium really does kind of belong over there. If I did the electron configuration of, I'll come back to helium. If I did the electron configuration of hydrogen, that's 1 electron, that's the electron configuration of hydrogen. And you just draw this 1 box, you would just have a 1 there. I go to the next atom, helium with a 2, and that's helium. It turns out that has the same properties as all the other noble gases. So chemists have taken the helium and drawn it over here, because by properties, all of these behave the same. But if I put it over here, it makes a little more sense, because notice, everything in this first column here, every one of these has everything full below it. Like, let me do, okay, there's hydrogen. If I want to do lithium just below hydrogen, it's 3, but watch what happens. The S has 1 in it, and everything else below is full. If I go from lithium down below there to sodium, its electron configuration is that. Everything below it full, 1 electron in the S orbital. And this would continue if I went on to potassium, I would have 1 in the 4s. So configuration-wise, all of these atoms in this column, they all have everything below full. You have an s orbital with 1 electron in it, and everything below it is full. That's true of all of these. All of these have 2 electrons in an s orbital, and everything else below it full. Meaning if I did helium, go back to helium, that's helium. If I want to go to beryllium that I've got below helium, because I've got helium cheated over there, that's beryllium. 2 electrons in an s orbital, nothing above, full below. If I go to magnesium, which is below beryllium, I'll have, oh, that should have been s orbital full, everything else below it. So where it is in the periodic table, except helium, because it's been cheated way out to the right side, everything in the periodic table, all the columns, their outermost shell has the same exact configuration of electrons. I mean, if I continue this and I jumped over there to boron, over here, well, let's go on to carbon, just so I have more below it. Let me go all the way to nitrogen. Okay, and nitrogen is 7, so I'm going to go 1, 2, 3, 4, 5, 6, 7. Nitrogen has 1 electron in each one of the p orbitals, and everything else below it full, and nothing above it. What's below nitrogen? Phosphorus. That's going to be up here. Phosphorus is going to be 3 electrons in each of the p orbitals, everything else below it. And when we went up to the 4 level, the 4p, which had 3 across, then we'd be down to number 33. So there is a direct correlation to the way that the periodic table is laid out to the way these levels are. Can you follow that? Direct connection to the periodic table. So if you wanted to continue this 1, 1, 3, 1, 3, 5 and fill out the rest of them, you could just go by the periodic table. Where was I with phosphorus? What was I going to say? I think that's enough. Oh yeah, I was going to do this. So let's go back to phosphorus. I was going to do this one more way to represent. So phosphorus was 15, 2, 4, 6, 8, 10, 12, 14, 15. Yeah, below nitrogen. So there's phosphorus. So this other way to represent it, if I did not phosphorus, but go all the way back down and up here down to 10, so we go from 15 down to 10, down to the next lowest noble gas, phosphorus down to neon, which is 10. That, if these 3 weren't here, or these 5 weren't here for phosphorus, then we would have the electron configuration of neon. That's what this represents. 1s, 2s, 2p, 1s, 2s, 2p. So instead of doing that, we will sometimes do this for the 3s2 and 3p. That's another way to do phosphorus. You just sort of bind one of the noble gases together, because that's the electron configuration of neon, and then you just add this 3s2, 3p3 on top of it. So now I've shown you 4 different ways to show an electron configuration. I tend to ask all like this. Your book does this. There might be some questions that have these boxes on D2L. And the quizzes I put on D2L. So electron configurations, this is how you do it. There's one more thing, okay. To expand this a little bit, I kind of wish I had the complete periodic table now. But let me try this. And I'll keep neon over here. We call these 2 columns S block, because in that, it was S, either 1 or 2 of them in S. In this column, it was 1 in the S, or 2 in the S. We call this section over here the P block, although helium really belongs over here in the S block. We call this the P block. When we get to these, that's when we start the transition metals. This is the beginning of the transition metals, and then I just said that's as much of the periodic table as I'll draw. So let me show you what happens if you build your way up there. We went, okay, hydrogen and helium, that's when you're filling the 1s. And then there's nothing over to the right, and you come back down and start at the next row. Notice this was the first row, and we were in the first shell, 1s. Now we're at the second shell, and that's where the 2s is, and the 2p's, 2p. What we'll do first when we're doing lithium beryllium, we'd be filling this, and then we jump over here to boron and start filling across, that's filling these. And after that, we'd be doing the third shell. Once you get over here to neon, you will have filled all of these. All right, keep going, we got to neon. Now we come back around to do sodium. And yes, next is the 3S. And notice we're back in the S block. We put one here and stop if it was sodium. We'd have two here if it was magnesium. And then we go from 12 to 13. Starting at 13, we're at the 3P. That's filling across here. And notice, when we were here, we were in the second row. When we're here, we're in the third row. And yeah, we're on the third shell. See what I'm saying? So you can read that 1, 1, 3, 1, 3, 5. You could build that on the periodic table just as well. And you're always going to have a periodic table to use. So you can get it from the periodic table. There are some aberrations here. We fill the 3P, and I told you there's a 3D, but notice we finish out the 3P, and we come over here, we're back in the S block at the fourth level. The truth is, this is 100% correct, except I left that one little detail. 1S, 2S, 3S, and you kind of wish the 4S was up here. Actually, it turns out the 4S starts right there. But if you're building this off the periodic table, that's what we would be at next. We did the 3P block, and then we came down, and we were at 4S, so yeah, that's what's next, 4S. So we build potassium and calcium. And then we start here. This first transition metal row is the 3D block. So the D's are like back one. S's and P's line up with what row you're in. The D's are, I guess, let's say they're down one. But the 3D block is where scandium, titanium, and vanadium start. So that's the 3D. The first row in the transition metals is the 3D. So that's what you get to next. Then you gotta get over here to the 4P. So 4S, 4P is next, just going across the periodic table, 4P, 4P, 4P. And if you kept going across the periodic table like that, you would get them in the correct order. It's just that this 4S, 4P, SP, DF, instead of being above here, it's shifted down a little bit where it overlaps. But 4 does have SP, D, and F, but everything starts overlapping up there. But you can still get the order if you just went across the periodic table. See what I'm saying? You could build this whole thing just looking at the periodic table. I'm going to stop here. We do get to 4P next. That's 4P. Then we come back over here to 5, and we're in the S block. So next would be 5S. You see what I'm saying? You could just keep going. But I'm going to tend to stay down here for the stuff we do. There is something weird that happens when you get to the d orbitals. I'm not going to go into it, but I can go into it just a little bit. I can go into these first three without running into the weird rules that start to happen. These simple rules I'm following, where you pair it, and then you go across, and then you go back and pair them. Weirder things start to happen up here. I'm going to leave kind of a dotted line to indicate that the 4S is right there, just to sort of indicate it. But again, if you're about to do an electron configuration, all the way up to the beginning of the transition metals, the 1, 1, 3, 1, 3, 5 will work. But starting here at 4S, things start to get weird. So I'm going to sort of keep the 4S here so we don't forget it. But let's say I was doing scandium, the first transition metal, 21. What I would end up doing is going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I did the 4S. 21. That's the electron configuration of scandium. And all of this would work the same, building the boxes across. This, the other way would work with the 1s2, 2s2, and then if it's scandium, I guess we could also use the argon configuration, and then for S, we could use 4s2, 3d1, s2, 3p6, 2, 3s2, 3p6, 4s2, 3d1. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 4s2, and then 3d1. So that's this form of electron configuration for scandium. There's this. But I'm just pointing out that once we get to the transition metals, that's when we start the D block. We're in a D block up here somewhere. So this is called the D block. The transition metals are called the D block. So again, if I grab helium and I drag it over here in this notch right here, those first two rows together, that's the S block. This block here, starting with boron in the top left corner, going down to the bottom right corner, without helium, that's the P block. This long part across here, the transition metals, that's the D block. And if you're wondering where the F block is, that's this junk that we're just squeezing down at the bottom here. But we're not going to go that far. These are all very rare. I mean, they have important uses. But fundamental chemistry, we don't tend to have exotic stuff like these huge, rare atoms. So we won't go as far as F, certainly. I think if I had you do any D, any of them that end in the 3D, it's just going to be one of the first three. And then we avoid some of those stranger rules that we run into. Okay, so I did give you guys, these are the ones I assigned for the exercises, but there are some on D2L. Lucy reminded me that I put that quiz up there, but I didn't realize I hadn't gone over this with you. But I think y'all can do that now. I think now y'all can do all of them that are on there.
Did you explain how to count the valence electrons?
Oh yeah. Oh yeah. Valence electrons are. Did I put any questions like that on there?
Yeah, I read like 4.
Okay. Let me look at it real quick. Quizzes. Testing practice. Electron configuration. What numbers are they? Oh, I should say electron configuration is synonymous with ground state electron configuration.
It's like number 12.
Okay. The valence for this one, I guess I could explain that looking at the diagram instead of looking at it written that way. I told you you've got the 1 shell, and you've got the 2 shell, and then these 3 go together for the 3 shell. You kind of ignore the fact that the 4 shell shows up here. These here, the furthest one out, the 4s, whichever one has the largest number, you take everything from that largest number, and those are the valence shell. Like here, the largest number here is 4. So there's 2 electrons in that valence shell. The 2 that are in the 4. So maybe it's better to use this to describe it. So it's all the electrons in the largest number in a diagram like this count for the valence. So this one has 2. That's right. You know what? This concept gets weirder than that. So what I would rather do, is there any other that say anything about the valence? Okay. I'm going to remove that question because valence electrons starts to become
Yeah.
it's an odd concept when it comes to
I
looking.
think that's it.
Is that the only one?
I believe so.
Let's just get rid of that one. If I think I want to come back to it, I will. There is one other thing to say about these. Was there anything about ions in there?
No.
I might come back to it, but let me just say it real quick. Let's go down to this lower level and deal with these. Electron configuration. I'm going to pick one of these from the first 2 rows. Let's say beryllium, which would be let me come back to it another time. Let's go on to, are those questions good now, Lucy?
Yes, sir.
Let's just stick with that for now. I'm too tired to do things on the fly. Did y'all read my update?
Yeah.
I do too well. I haven't had much sleep. My dad's done well for a couple days, but he's going to have to do well for a lot of days to make it out of the situation he's in. But the last 2 days have been good, so. So let's go on to gas evolution. So now we're jumping back up to chapter 8. I don't think I need this. I'm going to move this here. Oh, get. These screens weren't working this morning. I was having to work around that. But let me go ahead and do this PowerPoint that I've been building. Let me download the current form and I'll add something to it. So I'm going to go back up to chapter 8. So we've done almost all of chapter 8. We're to the point where we're actually talking about reactions now. So I'm kind of covering all the reactions, precipitation reactions, and then we did complete ionic and net ionic stuff. I covered acid base. It's this gas evolution reactions we'll do today, and I'll start again with oxidation reduction next time. And then we'll be done with chapter 8, and I'll do a little of chapter 9, and then we'll be done and ready for test 2. But I still got to get a lot of questions on D2L for you. Once I started reactions, I stopped putting those quizzes up there. Gas evolution reactions is what I want to cover. And what I want to put in there is this. Table 8.3, I'm going to stick in there. And there's only 4 of these. mind giving you that on the test. But a quick summary of what's in that table. I'll tell you what an intermediate is in a minute. But the intermediates are here. And the whole point, notice we're talking about gas evolution reactions, is I'll put a G here next to these, indicating that they are gases. It's just like before where I would put an S if it was a solid, and I would put an AQ there if it was aqueous. When it's H2O, we just put an L to say liquid. And that's it. You'll either see S, L, or G, solid, liquid, gas, or you'll see AQ indicating that it's aqueous, dissolved in water. Those are the 4 labels that we use. There are others, but these are the only ones that come up. Okay, let me tell you what this is. Very similar to the ionic reactions we were doing. Precipitation reactions. Let me find some examples here. I'll do that one next. Let's do gas evolution. Let's do these reactions for gas evolution almost always have an acid attacking an ionic compound. KOAH. KHCO3. And the question, the way you get these questions is finish the reaction, that is, draw in the products and balance it. Balancing is generally pretty simple with these. Any of this balancing that I'm having you do now is way more simple than the broader balance any equation I give you. So we'll do a little balancing for these. But okay, so the type of question you'll get is fill in the products and balance it. So if you fill in the products, you're always going to do this. H splits off into its ions, HCl. What's the charge on Cl? Cl's are -1, and the hydrogen will always be +1. So that splits into these ions. And this one, you just pop off the metal on the front. And if you don't know the charge on potassium, you just look at the periodic table, and it's +1. And then the HCO3 I'm going to leave together. And you can infer that that's -1. But that one is in that list of polyatomic ions. It's called bicarbonate. And I don't mind giving you that again for the test, so you won't get lost on what that is. But so these will split into these, and then you're going to go, okay, just like we did with the ions before, we're going to go this plus with this minus, and this plus with this minus. And those are going to be our products. So I'm going to have KCl plus, I'm going to go ahead and say aqueous. I think all of these end up aqueous for this. And then I'm going to write over here. Now I've got 2 H's, so this is H2CO3. Is it H2CO3? Yeah, because that was negative. Okay, good. So we have, this is one of our products, and you could go, okay, there you go. It's balanced. going to put a G on here for gas. It's balanced and there's the products, but that's not really the products. This is called an intermediate because as soon as that reaction happens, this is going to decompose. Yeah, I didn't need to put a gas there. I'm not going to put anything there because it doesn't really exist. As soon as this forms, it decomposes into this. Now this H2O liquid plus CO2 gas. That's the significance of this. When you see this, any of these three as your product, you'll have this chart, just recognize it and realize it's going to decompose into this. So really what I should have written here for the complete reaction, I shouldn't have this here. I should have this in place of the H2CO3. Meaning the real products here are H2O liquid plus CO2 gas. That's gas phase reactions. In some sense, that's all there is to it. I can do some more examples, but the whole point is if you have that as a product, you stop and go, okay, actually that's the product. And if you have that as one of your products, you kind of go, okay, actually that's the product. Oh, just so you notice, that is in that polyatomic ion list, and the SO3 is it's 2 negative. That's in the polyatomic ion list. It's called sulfite. And these two here, this one is NH4 plus. That's ammonium. That's in that chart, and so is OH, hydroxide. So these are all polyatomic ions. They're on that polyatomic ion list that you had for test 1. I'm not saying I expect you to pluck them out and remember it, but just so you know, we've talked about these before. They shouldn't be that foreign to you. And what else should I say? So anytime you have this, or this as a product, just realize, okay, that's not really the product. The product is really this. We get some water that just, and since these are always aqueous, there's background water there already because it's a solvent. So this just kind of disappears into the solvent and joins the solvent. The gas bubbles up and leaves the beaker. So in the same way that a precipitation reaction, we got one of the products to separate from the other one because it fell down as a precipitate. Gas is the same way, except it goes up and disappears into the air. So it sort of leaves the solution in the same way that precipitate does, except it actually leaves the beaker and floats away. Does that make sense? So that's gas phase reaction. I think you'll be able to do these. The only twist here is they give you some of these in words instead of giving you this, like it would say hydrochloric acid or potassium bicarbonate, and you're supposed to come up with a formula. On a test, I won't make you do naming again. I'm going to give you this so you can begin working with it, you know what I mean? So I think it's 73 and 74 that give you the names. I can give you the names, or you can just look them up or whatever, but that's extra practice. I hope to have practice questions like this on D2L, but maybe focus on 71 and 72 if you want to practice something between now and the time I get the list up. Let me go over this first one though. I skipped it for a reason because it seems very simple after I go over those. There is no intermediate here. If you pull up those examples for that one. Starting with an acid, these gas evolution reactions almost always start out with an acid and some ionic compound. Okay, and if you went, okay, it's an ionic reaction. I've got Br and Na. What I really have here, this is going to require some balancing. I have 2 NAs because of that 2, and 1 S, and it's 2 negative. Here I have an H plus and a Br minus. Okay, so to form the product, I'm going to take this plus and put it with this minus. But realize you've got 2 negative here and 1 positive, so I'm going to need 2 of those to make a charge balance. So I need H2S. So that takes care of these 2. Now I've got to put Br and Na together. That's 1 minus and 1 positive. So the formula is going to be NaBr, and the rest of this is balancing. I've got 2 NAs and only 1 Br, and I've got -2 here. What am I thinking? NA, yeah, okay. I've got 2 NAs here and 1 BR. What I need is another BR. So now I have NA, BR, NA, BR. NA, BR, NA, BR, NA, BR. So that's this, 2 NA, BR. And then to balance the rest of it, I've got 2 NA there. Since I need 2 BR, I'm gonna have to do that. That automatically gives me another one of these. And I think that's balanced. 2 H's, 2 H's, 1 S, 1 S, 2 NAs, and 2 BRs, and that's balanced. Okay, but again, there's no intermediate. This is aqueous. This is aqueous. This is aqueous, that dissolves. This is the G. So it's not like this further decomposes into something else and one of them's a gas. This one just, it's already there. So there's no intermediate, it goes straight to this. You guys okay? Since I didn't make y'all balance before, I probably should review that some and make some questions on those. I think it out this way, but if I didn't do all this, I think it might be, there's a simpler way to go through balancing. But that's gas evolution reactions. It's those 4 examples. You guys okay? We're still going to do redox and we're still going to do some heat capacity stuff from chapter 9. And I think what we'll do between now and the test is we'll have a week where we're just doing labs. There's some past labs we need to do. There's some makeup labs. So Monday and Wednesday, I guess not next week, but the next week maybe. We'll see how it goes. But I think we'll just have a week of lab days and we'll kind of get some labs out of the way. But we are kind of ahead. I mean, we're really caught up. So I've got the test scheduled November 5th. So there's still a good bit of time. So we'll just squeeze a bunch of labs in somewhere in 1 week. You guys okay? All right. Look at these, see if they make sense, practice them some. Go see Lucy if you need the help. I'm available too. Yeah. Oh yeah, I still got to work out the quiz too. We're still going to do it, I promise.